Okay, hello everyone. So today I will teach how to derive the equations of kinematics, the kinematic equations. So let's start with the first equations. Let's have the velocity time graph, which is where we will start with always, okay? Velocity time graph. And the first thing I want to ask is, what is the equation of a line of any line that is graphed? What's the equation of a line? Well, we know that the equation of a line, based on your math, is y equals mx plus b. Okay? But in this graph over here of the velocity time graph, which is y equals mx plus b? Well, first let's start with y. Y would be the y value of this point over here, the end point of your graph. And that one, as you could clearly see, is final velocity. Equals m is actually your slope. But recall, what is the slope of a velocity time graph? It is your acceleration, x. So if the y value was v final, what's your x value in this point? Well, we just have to project it downwards and we get t, or time. And finally b. B is your y-intercept. Okay? So the y-intercept would be this point over here, where it intersects the y-axis, or it intercepts the y-axis. Okay? The y-intercept, in this case, is clearly vi. So rearranging this, we get the familiar form of your first equation. Okay? So that's your first equation. Now let's go on to the second equation. We have here, as I mentioned, the plot of a velocity time graph. One other question that I could ask would be, what is the area under the curve of a velocity time graph? So this time we'll deal with area under the curve. Well, to get the area under the curve, I have some shapes here that will probably help us. So we can divide this, as we mentioned in our classes, into two shapes: the rectangle and the triangle. Okay? Now, first, let's go over the rectangle. How do you get the area of a rectangle? So the rectangle has an area of base times height. Okay? Base times height. What's the base of this rectangle? This one is clearly the time. Okay? The height of the rectangle, meanwhile, it goes up to that point, is vi. Okay, so vi and time. That's your base times height. Let's leave that for now. Okay, let's leave this. Let me underline it. But let's go into the triangle this time. Okay, let's work on the triangle. This time, your base would be still the same. This bit over here is going to be your time. But your height, it's not VF, because VF would be this entire thing. Okay, VF is the entire y-axis from 0 to VF. If you want this bit over here, we'll have to subtract VF minus VI to get this. So you subtract this thing by this thing to get this. Okay, so this is VF minus VI. Okay, area of a triangle, 1/2 base times height. Okay, so 1/2 base times height is equal to 1/2 times your base times VF minus VI. But let's go back to the first equation for just a split second. VF is equal to VI plus AT. We can actually rearrange this a little bit to get something that looks like VF minus VI is equal to A times T. So now you have something that can go into this place. It can substitute directly for that. So let's try it. If I were to substitute VF minus VI into the equation, I would get 1/2 times T times AT. I I just simply put that in there. Okay, so simplifying this further, we have 1/2 AD squared. Okay, so now we have VIT. We have 1/2 AT squared. Now let's recall. If we want to get the total area, that's going to be the rectangle plus the triangle, okay? Because this is just one bit, this is another bit. We need the entire thing. We need to add it up to get the entire area, okay? And if you recall, what is the area under the curve of a velocity time graph? Okay, it is actually your total displacement, change of x, okay, change of x position. And that is going to be equal to, what's the area of the rectangle? VIT. What's the area of a triangle? We just solved it. 1/2 AD squared. So this now is your second kinematic equation. Okay? So, now we have two equations. Let's go area under the curve again. Okay? Area under the curve. So let's go back to our graph. So we want to get the area under the curve. Again, another way to do it. But if you notice, this is not just simply a rectangle plus a triangle. It's much more than that. What if I ask you to get this shape over here? Okay, this shape that I am highlighting right now. Oops, that's a bit skewed, but you get the point. This shape over here is actually a trapezoid. Okay? And what is the area of a trapezoid? Okay? Area of your trapezoid. It is 1/2 times base 1 plus base 2 times h. Okay? That's the area of a trapezoid. Let's flip it a little bit like this so we have a clearer view of the trapezoid. What is base 1 and base 2? Well, the two bases are parallel sides. Okay? The parallel sides in your trapezoid would be this and this. Okay? These are your parallel sides. And that's simply VI and VF. Okay? So, 1/2, let's carry it down, VI plus VF. Those are your two bases. And what's the height? The height is your perpendicular side. And the perpendicular side to these two parallel sides would be this one. And this thing is your time. Okay? Time. So if we were to rearrange this again, we would get the area under the curve, which again is your total displacement. Those are equal. Is equal to VI plus VF over 2 times time. So that is your third kinematic equation. Okay, so now we have three equations. The last equation now calls for the use of this one. Okay, you will use what we solved in the previous item. However, if you notice, all of our equations so far, this one has time, this one has time, and this one also has time. All of them have time. But what if you're given a problem that does not have time? We need to find another way to get time. Okay? And the most convenient way to do it would be to use the first equation right here. Let me just fold the paper slightly so we get a good view of it. Okay? So, we can use this equation over here and play around with it a little bit to get a different form of it. Okay, let me just select a good color. So, we can play around with it to get time. VF minus VI over A is equal to time. And if you notice, this is actually your average acceleration. You just swap the A and the T. Okay, so now you have VF minus VI over A is equal to time. Now that you have that, you can actually move this bit over here Okay, this time can swap for this time. So now, if we were to write the equation again, like plugging this bit here for that, we were to get something that looks like delta x is equal to Vi plus Vf over 2 times Vf minus Vi over A. And that is your equation. But what do you notice about the top? Okay, the bottom is easy enough to simplify. It's going to be 2A. Easy. But the top bit, if you notice, what does the top bit resemble? Okay, this one is actually a difference of two squares. Okay, maybe Vf and Vi should be rearranged, but it's still a difference of two squares. So if we were to apply the difference of two squares, it would just simply be Vf squared minus Vi squared. And if we were to rearrange this, we could get the more familiar form, Vf squared is equal to Vi squared plus 2A delta x. Okay, so these four equations are now the backbone of your physics. For kinematic equations, Vf is equal to Vi plus At comes from the equation of a line. Delta x is equal to Vit plus 1/2 At squared comes from the area under the curve of the rectangle plus the triangle. This one, delta x is equal to Vi plus Vf over 2 times t comes from the area under the curve but of the trapezoid. And finally, if we rearrange that to have an equation without time, we simply get the fourth equation. Vf squared is equal to Vi squared plus 2A delta x. Now, which equation should you use in a given scenario? Now, if you notice, this equation, the first equation, does not have delta x. Okay? This equation, the second equation, does not have final velocity. The third equation, no acceleration, no A. And finally, this last one has no time. So, based on that, if you are given a problem and you are to list down the given and the required and you do not have delta x, that's probably a cue for you to use this equation. Same with this, if you do not have a final velocity, this if you do not have acceleration, or this if you do not have time. So, in solving problems involving horizontal motion using these kinematic equations, it's simply a matter of finding out which equation is most appropriate given your problem or given the scenario. So, I hope this video was very helpful for you, and good luck with your problems that you will encounter for horizontal motion. Take care.